Welcome back to Physics 40. This is lab for week 2 or lab 2. So I'm recording this ahead of time and hopefully it will work great. So I'd like to share my screen now. And okay, and the other thing I need to do is I want to switch over to the Elmo. Perfect. Okay, welcome back to Physics 40. This is week of August 24th, and this is the second lab. So this week we'll be doing an introduction to measurement, how to calculate uncertainty and error analysis. We will be studying statistical methods for error analysis using Excel and for multiple measurements. In the future, we'll be doing error analysis for single measurements propagating uncertainty. The pre-lab was to read the document on error analysis, and that's listed in the module on Canvas. Also to read over the lab and do a short problem. And all of that was due before lab. So this is the document here, a little picture of it. You can find all these documents if you haven't yet here in the Canvas for the second week of classes. And make sure you do that every week, that you check and you do the pre-lab before coming to lab, otherwise you'll be lost. So as you've already read, I'm going to briefly review what you've already read so that we can get to the lab itself. So this is lab. Physics is all about measuring. That's what we do. By nature, measurements can never be done perfectly, ever. There's an inherent uncertainty in any measurement, and it isn't just a limitation of your measuring devices. However, the more precise your measuring devices, then the more precise your measurement. So there's two concepts about a measurement. One is precision and the other is accuracy. We want to use these words all the time when we're discussing our results of our experiments. So precision is how precise your instruments are, like what decimal place they read to. Essentially, that's what it is. Accuracy is how close your results are to some expected outcome or known value. So we want to make sure we use these terms precisely and accurately. Ha ha ha. So in the picture here, this is all from the text and the reading. You can see, like, if you were shooting bullets at a target like this, you can see how, well, on average, the average of these 4 points is in the middle. So it has accuracy because we're considering the correct value or the value we want to be the center of the bullseye. But they're not very precise because the distance between the points is far away. Whereas in the second image below, you can see that it's not very accurate because they're not close to the bullseye, to the center, but they're very close together, so they're very precise. So we're going to be discussing this all semester long, and those two concepts are central to doing good measurements. We want both, right? The ideal is to have precision and accuracy. So just take a moment to, and I'm going to pause this. I want you to look at these different bullseyes, shot patterns, and to yourself determine whether or not you think they're precise, accurate for each one. So I'm going to pause right now. Okay, so hopefully you made a note of which is which. So for the first one on the left, it's neither. They're neither. It's not very accurate and it's not very precise. The second is precise, but since the collection of the data points is far from the center, it's not accurate. Here, that's both. This is your dream target, right? This is your dream data that you shoot right in the middle, and all your data points or your shots are very close together. And then finally, the data points or the shots are far away from each other, but on average, they're right in the middle, so it's accurate but not precise. I love this diagram because it gives you a visual of what precise and accurate look like, because we don't really have images like this when we're measuring things, but this gives it's a really good metaphor. So remember it. The only certainty in science and in life is uncertainty. And uncertainty doesn't mean that you're doing a bad job or that your results aren't accurate. It just is a fact of life. In fact, a measurement without a quantitative estimate of the uncertainty is meaningless. And that's something that's really important in all of science. So sometimes science deniers will go, well, you know, you're not 100% sure, you have uncertainty. Well, yeah, we have uncertainty because a measurement without uncertainty is not a scientific measurement. So it's very important. So you can never have an infinitely precise measurement. It's impossible. So it's unavoidable. Many classes use the word error. Error and uncertainty are interchangeable. I prefer to use the term uncertainty because error sounds like a mistake. So I want to use the word uncertainty. I think it's much more profound. We still do error analysis. I mean, they are interchangeable words, but I want to use uncertainty. So if you make a measurement M, then the standard way of representing your measurement and its uncertainty is M plus or minus delta M. Of course, the variable will be whatever it is you're measuring. If it was mass, it might be a little m, you know, or if it's length, it might be L or whatever, but it's the measurement plus or minus its uncertainty, and that gives you a range of values. And we want to know if the expected or true value falls within that range of values, right? If it falls within that range of values, then that's good, right? If your uncertainty is small, that means you have good precision. If you have a large uncertainty, then you're not precise. So, I mean, you could say, yeah, the length of my desk is, 3 meters plus or minus a kilometer, and the true value is going to fall within there, but it's so imprecise that it's not useful. So you want to balance that out. You want to have reasonable precision, reasonable uncertainty, and hopefully the true value or the expected value or the accepted value falls within those range of values. And we're going to be talking about this all semester. This is the point of lab, is to figure out how do you take measurements and estimate your uncertainty and then analyze the results. So one way of analyzing the results, or if I say compare to the expected value, compare means to calculate discrepancy and percent error. So some people use the word error for discrepancy. Discrepancy is how far off you are from the expected or the true value. I prefer the word discrepancy. I don't want one word, error, to mean 5 different things. So discrepancy is how far off you are. That can be expressed as in terms of the measure itself, or it can be expressed in terms of a percent. And we'll be doing both of those. So you can have a percent error, which is typically the accepted value minus this. I'm not noticing this isn't a good equation here. I need to fix it. It's the equation, or the definition for percent error is the true value minus the measured value divided by the true value times 100. And that is always absolute value. We typically round the percent error to 1 digit, as well as the uncertainty. Sometimes you might keep 2 digits for the percent error, but the uncertainty we always round to 1. That's how I want to do it. Some teachers do it differently. In other words, other labs do it differently. When you go to grad school and you start doing research, your mentor or your professor is going to tell you how they want to do the uncertainty. So in my lab, we're going to round to 1 digit. And, to tell you the truth, measurement theory is an art, and every scientist has their own methodology. They're all pretty similar, but the details will be different. So when comparing your measured value to a true or accepted value, you want to express the discrepancy, percent error, and if the true value falls within those experimental range of values. So for example, if you're estimating uncertainty with rulers, how do you estimate your uncertainty? So if you're using some kind of calibrated metric like this or scale, then typically what's done is you use 1/10 of the smallest division. So like, look at trying to measure the length of that bug body, there's some uncertainty in there. You can see like, well, you lined his butt up with the 0. That was good, but where's his head? So it's kind of in there. So you need to estimate what that is. And to tell you the truth, You use what you honestly believe. You are representing your confidence. You don't want to overestimate your confidence, and you don't want to, just make your uncertainty too large. You need to just give the most reasonable and honest result as possible. So in this case, I chose 1.55 inches plus or minus 1/10 of an inch. So, and so for example, like I'm not sure, so I kind of average or I interpolate between the values. So typically we'll kind of average between 2 points what this value is and then take the smallest increment. So if I'm looking at, and let me, you can see here, I'm going to zoom in. Like if I have a metric like this, and I could measure in millimeters and then take like, I can't see 1/10 of a millimeter. So I would probably do 1/3 of a millimeter or something like that. It's truly up to you. Sometimes you're measuring something that has an odd shape and you're going to have way more uncertainty. Now take out this, it's a lot easier to measure this width. Where's the length? I mean, it's a crazy thing. So I'm going to have much more uncertainty in the length of this eraser than I would in the width. So it just depends on what you're measuring, okay? So in general, when you're using anything that has like tick marks, or you're using a ruler, which is for the most part, metric stick like this, you're gonna just, it depends on what you're measuring and what you feel confident in. You're expressing your confidence. The next kind of measurement we typically make is with digital readouts. For this lab, we're using a gram scale, and it only goes to the 10th place. I don't know if you can see it there. So that penny weighs 2.5 grams. And typically what you do is you report your uncertainty to be half of the next digit. Because let's face it, you know how we round up on 5. So the scale's going to round up on 5. So like, is it 2.5 or is it 2.6? Like, what did the scale round to? So we just take that next digit. So I'm going to report 2.50 plus or minus 0.05. So I say, take the uncertainty to be half of the next digit. I like to say half of the unseen digit because it sounds more mysterious. Say, for example, you have, this is a digital caliper we'll be using. I mean, you're not going to use it. We would be using it. This has got a readout in millimeters. I love these things, they're so cool. So I'm going to turn it on and zero it out. And you can switch between millimeters and inches. So I can, put it in the caliper and then just read it out. It's flashing because the battery's low, which is very sad. But I don't know if you can see, it reads to the hundredths of a millimeter. So you can kind of see. So that means the uncertainty would be, I would say this is 23.440 plus or minus 0.005005. So use the unseen digit. And I need a new battery for that. Bummer. Okay. Any questions about that before we move on? I'll pause the video. Okay. There are different kinds of sources of experimental uncertainty, and typically when we're reporting or carrying out our experiment, we want to take notes about everything that's happening that's a source of our uncertainty or any kind of error. So you can have systematic error. So that's the idea that maybe the calibration's off, or the battery's bad, or you didn't level the equipment. So all the data will vary in the same way. If you go back to the, let me go back to this picture here. See in the second diagram, all of it's very precise, but they're all off by the same thing. So maybe, if I have some kind of gun, maybe it's cocked there at the wrong angle. It's not level. So they're all arriving at the same location. So I would need to re-level the gun in order to hit the bullseye. So you could see like this looks like a systematic error in that case. So let me go back to the slide here. And that's something we can fix. Okay, so you usually want to mention what your systematic errors are when you're carrying out an experiment, which I don't know if we'll get to do that this semester because we're not doing any real measurements. And then the other kind are human error, that is mistakes. So You want to record those as well and report those, but you know, often you don't want to just blanket say, yeah, sources of error for this experiment were human error. You know, like that means nothing. You'll get points taken off for that. That's like, because Johnny came stone to lab, right? So he messed up all the measurements. So don't, you know, so that's, we want to consider it, but you don't want to just have a blanket statement like human error, because it's dumb. Then there's also random fluctuations, and that's what we're doing today in the lab. And that's the idea that anytime you take a measurement, it's always going to be a little bit different, especially when you have repeated measurements. Very soon, we'll be analyzing the motion of an object that's dropped in free fall in order to calculate the acceleration due to gravity. Every time you drop a ball and you measure the acceleration, you're going to get a different value. And that's not because there's something wrong with the equipment. There's just random fluctuation with repeated measurements. It's the statistical nature of the cosmos. So when you have multiple measurements, to get the final value, you use the average. And then what I use in my class is average deviation. Other classes use statistical standard deviation or something. I don't use standard deviation because it's more complicated. There's a big chasm in physics between teachers about whether to use standard deviation or average deviation, and I want to use something that you can calculate from scratch, and that's average deviation. So when we have multiple measurements, you add up all the measured values and divide by the number. That's called the average. So we'll be doing that today, and we'll let Excel do that calculation for us. Then the deviation is how far every measure is from the average. That's called the deviation. And the average deviation is the average of those deviations. So it sounds like a lot of blah, blah, blah. In fact, I'm thinking how to edit this. Let me go back. I want to go back in the slide back to these. So what the average is you, like for the second diagram again, you can, well, let me take the last one. So the average of all these is dead in the center, right? But the deviation is how far each one of these data points is from the average, right? So these are all equidistant from the center, but you would measure the average is in the middle. So you measure that's the deviation for this point. That's the deviation for that point. That's the deviation, and that's the deviation. And then you would just average them all. That's the average deviation. So the standard deviation is much more complicated, and you'll get to learn that in another lab, but we're going to use average deviation for every single lab, okay? Here's the little example that I gave you, so hopefully you studied this. Say you performed an experiment in which you timed the fall of a mass, and you get the following values. So to do the average is add them all up and divide by 4, so you get 12.123, and 12.123 seconds is the average. To get the uncertainty, you find how far each value, or the difference, each value is from the average. So you go 12.24 minus 12.23, and so on. And then you add up the absolute values. You don't want to subtract anything. And then divide by the number, which is 4. So in this case, I get 0.064. So my final result is 12.23 plus or minus 0.006 seconds. Now notice, so the final measure is the average, and the uncertainty is the average deviation. Notice how the precision is the same. That's critical. You may say, like, how many sig figs do I report? I don't care about significant figures. I care about precision. So whatever your uncertainty is, whatever decimal your uncertainty lands in after you round to 1 digit, that's what you round your final value to. So you had to do this little problem. So let's pause for a moment and share what you all got for your result. And coming back. Oh, before we move on to the instruction for the lab, when you're taking measurements, and I hope we actually get to do one, because I hope everybody has a ruler that you can use, and I'm going to make up a lab that you can measure something around the house. You know, maybe we'll measure the density of a quarter, since we all have one, or something. But you want to make sure when you're doing measurements with meter sticks, especially, that you don't trust your eyes. Parallax is the idea that objects move. Like if you, for example, right now, put your finger in front of your face and close one eye, look at your finger, and now, put your finger, extend your arm out, hold on a second. Let me see if I can do this. So I'm going to show you something. Hold on. Okay, so here I am. So put your finger out in front of your face and close one eye, and be cognizant of the whatever's behind your finger. Now switch eyes. Close the other eyes. Notice how the background shifts. So the problem with that is when you're making measurements, you can be off depending on, with parallax, it can really mess up your measurement. So what you want to make sure that you do, and I'll just show you, is like when you're using a meter stick to measure things, you never want to be at an angle like this. Like say I'm measuring this, I'm trying to see it so you can see here. Like say I'm measuring, I wouldn't want to go like this. I want to be right over on top. I want to make sure I'm looking straight down, that there's no parallax, there's no angular confusion. And when I'm showing in these slides, like this is how easy our eyes can be deceived, because in this first case, all of these, they look like power poles to me. They're all the same length, even though they don't look like it. It's just because of what the background looks like. And then in the second image, the horizontal line, the vertical lines, they're the same length, even though they don't look like it's me. Same thing, like, and then this third image, the two lines are actually parallel, but because of the radiating diverging lines, they look bowed. And then get this, all of these are the same length. They don't look it at all. And then these lengths are the same. So you have to be careful, and with your eyes, because our brains are easily deceived. Okay, let me switch back to my thing here. Okay. All right, so now I want to talk about the instructions for the lab. Oh yeah, future lab. Okay, so you read the whole error document. Half of it is about single measurements and propagating uncertainty that way, and we'll do that when we do that kind of measurement. But today we're doing multiple measurements, so we'll do this next time, another time. I don't know when. This is the instructions. I hope you read them over. I worked very hard doing them. Gotta watch my time here. Okay, perfect. Okay, so this is how I want your lab report to look. It has to look exactly like this. I want your lab section, the date, who you are, and then your lab partners, and then the title. Okay, so just mimic this. I want you to mimic everything we're doing. Okay, so you'll be answering questions in your Word doc. You copy and paste them in. I'll show you in a minute what that looks like. So what we're going to do today is we measured a bunch of pennies, and they're all a little bit different. Some are super grimy and gross, and some are different years, so they're made of different alloys and whatnot. And I use this gram scale to measure it, and I'm giving you the values. So there's your 20 values for, this is 1 penny mass in grams, 2 pennies, 3 pennies, and so on. So what you're going to do is you're going to copy and paste that question. Don't wait. I'm going to put you in a breakout room. You're going to work with groups, but I want you to copy and paste the question and into your Word doc and answer it. And so it says, what kind of functional relationship do you expect between the total mass and the number of pennies? Is it quadratic, linear, etc.? Do you expect every penny to have the same mass? Just 2 little sentences, very short and brief. Please make it very clear what the question is and what the answer is. I want you to copy and paste them in so that it's easy for the graders to grade. Okay, and then see how there's a second one? So you'll answer that as well. So the first page of your Word doc will just be all the questions, and I'll show you what that looks like in a moment. But and then you'll have the data. I'm going to show you how to do the spreadsheet in a moment. So you'll do 1 through 20 and then the mass. Oops. Okay. All right. So the first thing we're going to do is find a value for pennies by averaging all of the masses for all these different measurements. In other words, like we're going to make a column here, and I'll show you how. So you take, this will be equal to the total mass divided by the number of pennies, and so on. This is all made up fake data, not the true values, because I wanted to show you a sample, but I don't want to give you all the answers because I want you to work on it yourself. And we should all have the same answers with the real data because we're using the same data. So what you do is so they're all about 2.5-ish. So we're going to average them and then get the average deviation. Notice if I round the average deviation to 1 digit, it's 0.2. So then I'm going to round the average to the same number of digits. Now, Excel will give you as many decimals as you ask it to give you. So don't ever show me more than this many. In fact, this is too many already. You should round that to something reasonable. Since we're going to round to only 0.2, like you might want to round these larger digits to 4 sig figs, because we really don't need to know what it is at the nanoscale. Okay, so here's everything you need to do this, but I'm going to show you how. So these are the equations you need, and I'll show you how to do that. And then I give you instructions. You must follow the instructions step by step, because when I show you, I'm going to go at warp speed. So, and this explains everything and how to do it. So what we're going to do is find what 1 penny is. So I found this to be 2.2 plus or minus 0.2. And then 100 pennies, I just multiply both of these by 100. So I'm predicting how much 100 pennies would weigh based upon this average that I obtained from the 20 pennies. All right. And then we're going to find the mass of 100 pennies by graphing. Okay. So a better way to estimate the mass of a single penny is to actually plot the data. So if you've never done a linear fit in Excel, now you have a chance to. So I'll show you how to do this in a moment. I'm going to do the whole thing for you fast with the fake data. So you highlight the columns, and then you can insert a scatter plot. So this is how you do it. And then you're going to label the chart. You need to display an equation, and it should look like this. So you're going to select chart elements and label everything so it looks exactly like this. And then you'll use the linear fit to find the value for a single penny. And I ask you a bunch of questions, and you could follow all of this and answer the questions. This is what finally your data should look like. So you're going to have a linear fit. I ask you what the slope is. Well, this is the slope. The slope is the mass of 1 penny, right? And then here's my calculation. I'm using this equation to calculate the mass for 100 pennies. And then I get a % error between these two, taking this as the true value, and then I calculate my uncertainty, and I round it to 1 digit, so I get about 20% error between the two values. The true data that I'm giving you, which is here, the true data, which is this, gives you a much better result. Okay, because I just made this fake data up. Okay, so then what you're going to end up turning in, you're going to read all the instructions. It looks like this. Your first page will be, here is the title, and here's the header. That's a point. Here's the first question. I just copied and pasted it, and you can answer it. If you want to answer it in a color, that would be nice. Just make sure it's set off from the question. And so you have, and they're very short, so you can fit it all on the first page. And then the second page is your data. And this is the real data, actually, which I you can check and make sure you have the same. All right, so I'm going to stop my share. Let me check the time. Okay. All right, so, okay, I'm going to share my Excel spreadsheet. Okay, so I already put the data in the spreadsheet. And if you have a Mac, then you can use Numbers. If you have Google, you can use Google Sheets, or you can use Excel. So I'm using Excel. And so let's just pretend we typed in the numbers. So you need to type in the numbers. And then, so I'm going to you're going to title everything. So this is the number of pennies. And then this is the mass. And when you do the mass, you need to show the units, and it's in grams. So you always use a parentheses like that. You don't want any letters in the Excel cells. Okay, so these are the columns, and these are the cells. So you can see that cell is B3. See over here it says it's B and down 3. So this is identified. That's B4. That's A2, right? So I can go 1, and then I'm going to type in 2, and then I type in 3. If you put 3 numbers in, and then you put your cursor in the corner, notice how I have a big fat white plus? I can put it in the corner, turns into a black thin plus. If I drag it down, it will fill it in. Oh, darn, I didn't want to do that. How do I do that? Let me see, I go like that, and I'm going to fill it in. There you go. So I had to highlight 1, 2, 3, and then put my cursor in the corner and drag down, and it fills it in. And that's awesome, because it would do it for 1,000, or would do it for whatever. So notice here, we're all used to all these kind of graphical icons. So I'm going to center everything. There you go, nice and pretty. I must have borders. So you border it. I know there's going to be another column. So you highlight this, and this is the border. So see bottom border, I want all borders. It's hard to see otherwise. So please, borders are worth the point. And then this is going to be the average mass. Average mass. In other words, in grams. So what I'm going to do, watch how you do equations. You go equals, and oops, that's not equals, equals. What you do is you click on the cell. See how it shows up A3? Divide by, oh no, I did it the wrong way. Sorry, I wanted, the average mass is going to be the total mass divided by the number. So I go, click on that and divide by that. Enter it, and then I drag down. So notice what happens is if I put my cursor in the corner and I drag it down, it copies the equation, but then changes it. So here it's B3A3, here's B4A4, here's B5. I'm in Power Tool. I'm going to highlight it, I'm going to center it, and I'm going to this has way too many sig figs. So what I'm going to do is you can go to, see where the zeros are? I can decrease the number. That's too much. I'm going to just have 3. There you go. Now look, I have 4. That's good. So there's my data. So here, now I want to do the average equals, and the equation, which is all in the instructions, is the word average. So notice how it tells you what to do. It gives you the thing. I'm going to highlight the data that I want and then close the parentheses. And notice how it says up here at the top, C3 to C22, and that's exactly what it is. Okay, there's my average. And then I want to get the average deviation, which is avdev equals avdev. Oops. Shit. Oops, I swore in class. So the equation is avdev, so you have to have the equal sign. I'm going to highlight the data, do not include the average, and then close the parentheses and enter. And there's my data. I'm going to center that. Okay, so then how am I going to report this? I round the uncertainty to 1 digit, and then, so which is 0.04, and then I'm going to round the average to the same precision. So it looks like I'm going to get 2.61, right? Plus or minus 0.04. Always have a leading zero. That should be a minus 0.04. So this is like, so I'm going to click on this and notice it's up here at the top. And I want to say M is equal to, and then I could do a parentheses around the whole number and do grams. Now I know I'm going through this fast, and it's okay because you can slow this down later. You can watch it again. They will delete this after 30 days, so you need to like learn how to do this. We're going to have a final exam where you have to set up a spreadsheet and do this kind of analysis, which is, you can do. It's going to be fine. You can do it. So please pay attention. Don't let your lab partner do it for you. Everyone's doing their own work today, even though you're going to work in groups, just to check with each other and make sure you're getting the same results. All right, so if I'm going to calculate the mass for 100 pennies, I'm just going to multiply that by 100, mass for 100, and I get, and all these instructions are in the lab report. So you're going to follow that lab report step by step. So it's going to be 261 grams plus or minus what is 4. Oops, I keep on doing 1 instead of 4. I'm going to parentheses grams, and I'm going to, I don't like that form, I'm going to go like that. So you could do the parentheses around the whole thing, and that's kind of nice. And you don't have to import any fancy, you could just do plus or minus, that's absolutely fine. So that's my prediction given this. Now, the second way is you do a plot. So I'm going to plot number of pennies versus mass. So you highlight the columns, and then you go up into insert. And then over here, I got all these plots. So what I'm going to do charts. I'm going to do a scatter. Hey, hey, hey. And then I right mouse click, and down it goes add trend line. Right mouse click on the data, add the trend line. And over here on the right, you get all these options. It knows it's linear. You could do polynomial, which is crazy. You could, but I'm going to do linear. And then at the bottom, display R-squared value, which tells you how good a fit it is. You have to Google it. It's part of the instructions. And then display the R-squared value. Grab it, move it out of the way. You can highlight the text. Now it's all formatting. And I'm going to go to home. I'm going to make it bigger, 14, so I can see it. That's pretty nice. There's my equation. And then if you click on this thing, chart filters, no, not that, this guy. No, not, style, not that. So now what you want to do is add the, hold on, you want to add the labels. And for some reason, hold on, you're going to figure that out. I have it in the instructions, and I'm kind of running out of time, so I have to stop. So then you and your lab partners are going to figure out how to label this thing. This is a new version of set a style, color scheme for your, now I'm just being silly right here. Text options, so you're going to click around so you can figure out how to label. That's your job. That's the thing I won't tell you how to do. And then now you can see what the value is for 1 penny. So 1 penny has the mass of, if I round to the same digit, we don't really have a way of getting uncertainty here, so we're not going to bother. I got 2.66 grams. And then for 100 pennies, I'm going to use the entire equation. So you can just write it out. I'm going to have 2.661 multiplied by 100 minus 0.2753. Boom. And then actually you can put this as an equation. You can go equals. I want you to write it out, and then you can go 2.661 asterisk is multiplication minus 0.2753, enter, and then you get that. Okay, so then you need to do the percent error. And so you know that you're going to, this would, if we round to the same number of digits, then this is going to be approximately 2.66. Yeah, rounding up to the same precision as this guy, just for the heck of it. And then you can go, this is going to be equal to the quantity 66 minus 261 divided by 261 times 100. And that is about, I'm using tilde, 2%. And that's your lab. So you can use, I'm a big fan of trim. And so I use the snipping tool, and I'll just grab that whole thing. When I'm done, I didn't finish labeling the chart. You need to do that yourself, and then copy and paste that into the Word doc. And that's it. So I know that was fast and furious, but I'm here to answer your questions, as are the lab assistants. So have fun. See you later. Bye.